It is a great pleasure to welcome my good friend Bob Yunken to speak in the seminar. He'll speak on the Helffer-Nourrigat Conjecture, Hypoellipticity of Polynomials of Vector Fields.
Thanks very much, Nigel. Yeah, and thanks for the invitation. I'm going to reduce the video of participants on my screen, so if anyone has a question that I miss, maybe Shang or Nigel can yell at me, or Nigel can croak at me, or just make some other loud noise. Feel free to interrupt. Yeah, so the point of this talk is really to talk about the hypoellipticity problem. So I'll start by reminding you what hypoellipticity means, but it could also be interpreted as a talk about Fredholmness as well, because the two properties are extremely closely interrelated, as we'll see shortly. So let's jump straight into it. Yeah, so we need to start with what hypoellipticity is. And here's the definition. So I start with a smooth manifold M, and I'll say that a differential operator, a linear partial differential operator, P on M, is hypoelliptic if this differential equation Pu equals F, where U and F may be distributions, has this smoothness of solutions property, so that if the right-hand side F is smooth on a certain open set V, then any solution U for that equation will also be smooth on the same open subset V. So this is, as you all know, this is a property of elliptic operators, but it's there are many non-elliptic operators as well that also have this property. And it actually, I mean, the one way to prove it for elliptic operators is to prove Sobolev estimates. So the a priori estimates for an elliptic operator will allow you to conclude this smoothness of solutions property. And in that case, if we do have these a priori estimates, Sobolev estimates, we'll call it not just a hypoelliptic, but maximally hypoelliptic, which is kind of the nice case. And that shows you instantly why this is related to index theory as well, because if you have Sobolev estimates, then if your manifold is compact, then you'll get a Fredholm operator. And so you could ask questions about what its index is and whether there's a formula for this index. Okay, but that's not what I'm going to do. And I'm not even going to work much on manifolds. For the question of hypoellipticity, there are interesting questions even just on R2. So let's start with some operators that you all know. Here's an elliptic operator, the Laplace operator, and this is hypoelliptic. And as you all know, if we, so an interesting case would be to take in this equation back here, I could take f to be 0. And in that case, I'm looking at harmonic functions, and we all know that harmonic functions are smooth. So this is an indication that this is a hypoelliptic operator. And the same thing goes for the heat operator. This is no longer elliptic. But nonetheless, we know that the heat kernel is always a smooth, which means that you always have smooth solutions for the heat equation as well, as soon as the right-hand side is smooth. And to give you a non-example, let's take the wave operator. So again, if the right-hand side is 0, in this case, there are many waves that are not smooth, square waves, sawtooth waves, whatever you want. You can get horribly weak solutions to the wave equation, which are perfectly good solutions even when the right-hand side is 0. So this is far from being hypoelliptic. But then you can get more interesting things happening as well. So here we've got a version of Bismuth's hypoelliptic Laplacian. And this guy is interesting because it's got this x coefficient here, which means that when x is 0, this term vanishes. So it's really only differentiating, or it seems to be only differentiating in the x direction, purely in the x direction when x is equal to 0, so along the axis. But nonetheless, it manages to be hypoelliptic. And to give another interesting example, show you how subtle this question is, you could look at this Grushin sublaplacian, minus d by dx squared minus x squared d by dy squared, plus some lower order terms. So the first two terms are order 2, and the third one is seems to be order 1, with some coefficient alpha, some complex constant in front of it. And you see, as you see in the work of people like Eric van Open, Raphael Ponge, and many people preceding them, you see that the hypoellipticity of this order 2 operator is dependent on the order 1 term. to be precise, this operator will be hypoelliptic if and only if the coefficient alpha is not an odd multiple of I. So this is already an indication that something extremely subtle is going on with this hypoellipticity problems. It's not simply a manner of telling which direction things are differentiating, because the usual slogan for ellipticity is that an elliptic operator is something that differentiates in every possible direction. Here, there's something similar going on, but it's a much more subtle question. And so the big question underlying this whole talk will be, what is it that governs hypoellipticity? And the answer was provided by, well, an answer in extremely general circumstances, let's put it that way, was provided by Rockland and proven by Helffer-Nourrigat, and then conjectured in even more generality by Helffer-Nourrigat in yet another conjecture, which I'll talk about shortly, and then partially proven by Helffer-Nourrigat in following work, and in continuing work with Yakovos and Omar, we've managed to find a proof of this Helffer-Nourrigat conjecture using groupoid methods going back to Kohn and Debord-Skandalis, and which gives a really satisfying non-commutative geometric type of explanation of what it is exactly about these operators that makes them hypoelliptic. That said, Helffer-Nourrigat had already understood the basic philosophy. The basic philosophy is that when you're dealing with these kinds of operators, so the kinds of operators I'm looking at here are polynomials in some vector fields. And when you're dealing with these kinds of operators, you need to understand the representation theory of some oscillating nilpotent Lie groups. So oscillating nilpotent Lie groups here will play some non-commutative version of the tangent bundle. And that's so like I said, Helffer-Nourrigat had already understood that the representation theory of these nilpotent Lie groups is the determining factor for hypoellipticity of these kinds of operators. Okay, so I need to say a little bit about what the Helffer-Nourrigat conjecture is. I'm going to do it fairly quickly on this slide, and then we'll come back to it later in the talk. So I'm going to start with just a family of vector fields, V1 up to Vn on my manifold. I should probably ask that these vector fields satisfy the bracket generating condition as well. So this is sometimes called Hallmander's condition. And what it says is that if you take repeated brackets, Lie brackets of these vector fields up to, say, depth at most some finite number, capital N, then those repeated Lie brackets of vector fields will span the tangent space to M at every point. So we're not asking that V be a frame for the vector bundle, but we're asking that if you take repeated Lie brackets, then you get a generating set at every point of M. And using this Helffer-Nourrigat in their very broad conjecture, start by constructing what's now called an oscillating nilpotent Lie group, which I'll describe later, and is called GR F of P in this talk. And then they construct also a particular family of unitary irreducible representations of this family of oscillating groups. And these choices of which unitary representations pop up is very interesting. That's sort of the key point of the Helffer-Nourrigat conjecture, is which representations are the ones which are relevant for the hypoellipticity problem. And they depend on the singular geometry of these vector fields in a way that, like I said, I'll describe later. And then they conjectured that a polynomial P in these vector fields, so that gives you a differential operator on your manifold, will be maximally hypoelliptic if and only if the representations of certain frozen coefficient operators, which I'll have to tell you what they are later, but essentially you take P, your polynomial in these vector fields, and you freeze them in such a way that it gives you now an element of the universal enveloping algebra of the Lie algebra of the oscillating nilpotent Lie groups. And thus you can represent it as an unbounded operator via any irreducible unitary representation of the group. And the condition is that this give you a left invertible unbounded operator on the smooth vectors inside your representation. For every one of these irreducible representations in this family specified by Helffer-Nourrigat, which I've called HNF, and I'll refer to this HNF as the Helffer-Nourrigat cone, because we'll see that it has a cone-like geometry shortly. Okay, so a lot of this talk, I'll need to explain what this cone of representations is, what this HNFP is. But for the moment, let's just say Helffer-Nourrigat had already figured out which the right set of representations are, and such a way that when you apply these representations to the frozen coefficient operators at every point, you, if those are all left invertible unbounded operators, then your operator is maximally hypoelliptic. Okay, so like I said, this square brackets PP notation here means any image of a polynomial of vector fields as a polynomial of frozen coefficients, so left invariant vector fields on our Lie groups. And I say an image because, in fact, in the context of the Helffer-Nourrigat conjecture, it's not unique. There are various different images that you could choose, but what we will see, I guess that's too soon, what we'll see is that the choice of representing element will not affect the operators that you get. That is, under any of the representations within the Helffer-Nourrigat cone, any image will give the same unbounded operator as its representation. Next thing to say, and Helffer-Nourrigat wouldn't have said it like this, but their construction is basically a deformation to the normal cone, or some kind of dual to a deformation to the normal cone. So it's very much related to things that Kohn and de Bord-Scandalis and other people have done. And what this means is that we can prove the conjecture by using methods associated to groupoids, tangent groupoids, deformation to the normal cone groupoids, and using this approach to pseudo-differential calculus, which is basically pioneered by Kohn and de Bord-Scandalis, and then carried on by Eric van Elp and myself and various other people. Okay, so that's what I need to tell you about in the remaining part of the talk, but maybe I'll just pause there and see if there are any questions at this moment. Right, then let's head on. So now I need to tell you about what this groupoid approach to pseudo-differential operators is. So this part of the talk, some of you may have already seen. I apologize for you, but for those that haven't, it's important to go through it. So here we go. Let's start with the classical calculus. And in fact, let's start with a bit of philosophy. What is a pseudo-differential calculus? Philosophically speaking, a pseudo-differential calculus on a manifold M is an extension of the n-filtered algebra of differential operators to a z-filtered algebra, or you could even take an r-filtered algebra, let's take z-filtered algebra of operators with three key conditions, properties. The first is regularity, that is, the operators of order minus infinity should be smoothing, the operators that sit inside every gradient, every level of the filtration. The second is pseudo-locality, which is that the Schwartz kernels of these pseudo-differential operators should be smooth off the diagonal. And the third is that we should have parametrices, so that if I have a differential operator with some invertible principal symbol, in some sense yet to be made precise, then there always exists a parametrics Q of order minus M, and this is precisely why we need to extend to negative orders. So there'd be some Q such that it's an inverse to P modulo smoothing operators. These are the three things you want from your pseudo-differential calculus. Perhaps also you could add the existence of limits of asymptotic expansions. That would be a useful thing to have as well, but let me skip past that for the moment. And why do you want these three properties? Well, the basic point is that if you have a pseudo-differential calculus satisfying the three basic properties, then you automatically get elliptic regularity. That is, invertible principal symbol of a differential operator implies hypoellipticity. And here's the proof in one simple equation. If you have this equation, differential equation PU equals F, you can write your solution U as, in the standard way, 1 minus QPU plus QPU. And the left-hand guy will be smoothed by the regularity assumption, while the right-hand guy will have the same singular support by the pseudo-locality condition. The fact that it's the singularities of the Schwarz kernel are only on the diagonal means precisely that when you apply Q, there's no propagation in the singular support. There may be propagation in the support, but in the singular support, there'll be zero propagation. So we get precisely the condition that we need to get hypoellipticity out of our parametrics. Okay, so we're looking for ways to construct algebras, extensions of differential operators, which satisfy these conditions. And this is where groupoids come in. So here are two of the greatest ideas of the last 50 years. The first you know very well. Almost everyone in this virtual room knows the existence of Con's tangent groupoid. It's an ingenious device which allows you to combine a pseudo-differential operator and its principal symbol as the restrictions at t equals 1 and 0 respectively of some deformation family. So Con used this famously to prove not just the index theorem, but also the index theorem for foliations. And of course, countless people over the years have generalized Con's work to produce index theorems for all sorts of other geometries, with boundaries, with on Heisenberg manifolds, all sorts of other wonderful geometric constructions. Okay, so that's the first brilliant idea. But then the second brilliant idea is that you can reverse engineer this, not just so that given a pseudo-differential calculus, you can create these deformation families, but that given the deformation families, you can produce the pseudo-differential calculus. That is, you can characterize precisely the deformation families that appear from pseudo-differential operators using a canonical R cross plus action on the tangent groupoid. And this R cross plus action is due to de Borden's-Condelisse. They're the ones that realized, sorry, it's not due to de Borden's-Condelisse. They're the ones that realized how useful it is for pseudo-differential operators. It existed well before, well, even before Con, but it was really de Borden's-Condelisse that realized that this canonical R cross plus action on the tangent groupoid is precisely what you need to define a pseudo-differential calculus. And to justify this idea of de Borden's-Condelisse, let's start with something much simpler, just about polynomials. So a basic fact from commutative algebra it says that there's a one-to-one correspondence between all polynomials on Rn, so in n variables of order at most m, and homogeneous polynomials, so of degree constant equal to m on one dimension larger. The way this works is, well, if you're given your homogeneous polynomial, which has now n plus 1 variables, where I'll call the last variable t, you can simply restrict to t equals 1, and that gives you obviously gives you a polynomial of order at most m in the other variables. Obviously, it's well known, there's an inverse to this restriction map as well, where given an inhomogeneous polynomial of order at most m, you can just add appropriate powers of the extra variable t so that it becomes homogeneous. So the amazing thing is that this same principle works. Oh, sorry, before I go on, yeah, let me say that if instead of restricting at t equals 0, you were to restrict at t equals, sorry, instead of restricting at t equals 1, you were to restrict at t equals 0, you would just get the highest order part of your original polynomial A. And yeah, so the amazing thing is that this same principle works for polyhomogeneous symbols in the classical pseudo-differential calculus. So let me just remind very quickly what a classical pseudo-differential operator is in the world of people like Hollmander. It's given by an oscillatory integral formula. So you take your function f, you take its Fourier transform, you multiply it by some symbol function a of x and psi, and then you take its inverse Fourier transform. So that's a very simple principle, but you need to be quite careful with what you're allowed to use for your polyhomogeneous symbol for your symbol AX psi. If you just use any old badly behaved function, this operator may not be well defined because the Fourier transforms will be poorly behaved, will not converge, for instance. So you need to put some restrictions on what class of symbols we're allowed to use, and to write down the full definition of this would take me a couple of pages. As anyone who's learned what a pseudo-differential operator is knows, you need to start by defining simple class functions given by some decay estimates on derivatives of A at infinity. And then once you've done that, you need to define what an asymptotic expansion is, and you need to say what convergence of asymptotic expansions means, and then you want to define your A to be a limit of a polyhomogeneous expansion of symbols in some sense that generalizes the notion of a polynomial in Xi, but where you're allowed terms which are not just positive integral powers of Xi, but maybe homogeneous of negative or fractional values as well. Okay, so I won't write down this definition, but I will say that there's a cute little fact which my PhD student Nathan Couchet has proven following work by Van Erp and myself a few years ago, which is that you have a theorem very similar to what you have for polynomials, almost identical, in fact. So I've simply replaced in this theorem polyhomogeneous polynomial with a polyhomogeneous symbol on the left. And on the right-hand side, I've just added the word modulo Schwarz. And you get exactly the same correspondence. So here, what does mod Schwarz mean? Homogeneous mod Schwarz means that if you dilate this function by multiplying the Xi and T variables by S, you just get the same function multiplied by S to the power of M, but not on the nose anymore, modulo some smooth function which is of Schwarz decay in the variables Xi and T. Okay, so it's a very simple modification, but it turns out it characterizes precisely the definition of Cohen and Nuremberg of a classical polyhomogeneous symbol. Any questions on that? Because it's maybe a good point to pause, take a breath. In which case, let's plow on. So yeah, what do we have? Let's draw a picture of this. So my A underline, apologize for the subtlety in notation, my A underline is now a homogeneous function on M cross Rn cross R modulo Schwarz, where polyhomogeneous is with respect to these green dilations here. What the previous theorem says is that if I restrict to this red line, so I restrict to an affine subspace, you can immediately see that because the red line is not stable under the dilations, you will not end up with a homogeneous modulo Schwarz function on the red line, but it turns out you arrive with what you get as a polyhomogeneous symbol on the red line nonetheless. On the other hand, if you restrict to the blue line, which is stable, you will get something which is homogeneous modulo Schwarz, from which you can extract a homogeneous component on the nose, and that is precisely the principal symbol, the principal part of your polyhomogeneous symbol on the red line. And then if instead of working with symbols, you want to work with kernels of operators, you can simply take the Fourier transform in the Xi variable, and what you get is this. Fourier transform replaces infinity with zero. It interchanges infinity and zero, so that the dilation action that we had above becomes this hyperbolic dynamical flow on the bottom. And you get exactly the same theorem, but now the restriction to the line at t equals 1 will be the kernel of the polyhomogeneous pseudo-differential operator. And the restriction to the blue line will be what I call the principal cosymbol, which simply means the Fourier transform of the principal symbol. So this is now some distribution, some homogeneous distribution on the tangent bundle, whose invertibility will determine ellipticity for the operator with kernel given on the red line. Okay, so now we have this picture. So why do I prefer this hyperbolic dynamics here? It's because that hyperbolic picture is actually coordinate independent in the following way, that I can take this picture, which I just drew, and overlay it on the tangent groupoid. So I think in this audience, I'm going to assume that everyone knows what the tangent groupoid is. So let me just draw this picture and tell you, once you see this picture, you can immediately guess what the Debord-Scondalis action is. It's just rescaling in the t parameter when you're at t non-zero. So you just move your copies of the pair groupoid left and right by multiplying by t. Multiplying by lambda, say, where lambda is some positive real number. And this glues smoothly at t equals 0 to the dilations on the tangent bundle. So that you get this hyperbolic dynamics on the tangent groupoid. And as we've just seen, when you take a distribution, in a sense that I'll have to make precise in just a second, when you take a distribution on this tangent groupoid, which is invariant for this green Debord-Scondalis action modulo smooth Schwartz class functions, then the restriction at t equals 0 will give you precisely the kernel of a pseudo-differential operator in the classical calculus, and the restriction at t equals, what did I say? The restriction at t equals 1 will give you a pseudo-differential kernel, and the restriction at t equals 0 will give you its principal cosymbol. Okay, so this I include in case anyone has not seen the tangent groupoid before, but I think I'm going to assume that this is not the case here. If anyone wants me to talk about that, we can talk about that afterwards. So now, instead of making this a theorem, we can make it a definition. We'll say that a properly supported classical fully homogeneous pseudo-differential operator of order at most m on the manifold M is an operator whose Schwartz kernel kxy is the restriction at t equals 1 of some distribution k underline on the tangent groupoid, in a sense due to Lescure-Manchon-Vassou, which I'll say a couple of words about in a second, which is homogeneous of degree m modulo smooth properly supported functions for the Debord-Scondalis action. And I've written down what the Debord-Scondalis action is here. It's exactly what I described on the previous slide. So what's this Lescure-Manchon-Vassou sense of a distribution on a groupoid? It's actually not a distribution in the general sense. It's rather a family of distributions on each of the fibers, say source fibers. Oh, sorry, here I've taken E prime R, so R for range. So this is a family of compactly supported distributions on each of the range fibers of the distribution, which vary smoothly from fiber to fiber. And again, given that much detail, you could probably guess what the appropriate definition is. In fact, there's about 3 or 4 different possible definitions for what this is. And Lescure-Manchon-Vassou have studied very carefully what these various different definitions are and the relationship between them. Yeah, so maybe I won't say anything more about that for now, but just this is a well-studied family of distributions. And then the theorem is that this definition, as I said, is exactly equivalent to the usual definition of classical pseudo-differential operators, and that the restriction at t equals 0 gives you the principal cosymbol, or at least you have to extract the purely homogeneous part of that, but that's a minor technical issue. Okay, so this gives us a new groupoidy non-commutative geometry type of way of defining pseudo-differential operators. That means you don't have to read all those old books of Trev and Taylor and so on about simple class functions and asymptotic expansions. You can, as soon as you know what a groupoid is and what a distribution of a groupoid is, then you can define pseudo-differential operators in just a couple of lines. Okay. What can we, yeah, so there's more structure to this. So just as you can convolve two ordinary distributions on a group, say on Rn, likewise you can convolve two Lescure-Marchand-Vassou type distributions on a groupoid, given by exactly the usual formula for a convolution product interpreted in the groupoidy way. So classic examples would be the pair groupoid, for which the product law is given as follows. And by simply turning that into an integral formula, you obtain a convolution product on the pair groupoid, which is precisely the rule for the composition of Schwartz kernels of singular integral operators on M. So that Lescure-Marchand-Vassou's groupoid law is recovering precisely composition of operators on C infinity M. Another thing that you could do is take the groupoid, which is the tangent bundle, where the group law is now just given by fiberwise addition. And again, if you, that should be a VP on the left, obviously. Again, if you turn that into an integral formula, you get precisely the convolution product, fiberwise convolution product on the tangent bundle. And of course, if you take a Fourier transform of that so that you're talking about symbols instead of co-symbols, this convolution product just becomes pointwise product. And so this is precisely the formula for the Fourier transform of the product of principal symbols. So of course, Conn knew all this. This is what Conn used to deform pseudo-differential operators into the principal symbols. But it's nice to realize that in this framework. Yeah, so what we see is that this groupoid convolution law describes both composition of CIDOs and the product of symbols. And now we would like to prove this elliptic regularity theorem. So for this, we start with a differential operator. We say it's elliptic if its principal symbol is invertible outside 0, which basically means that its convolution product of its co-symbol at t equals 0 will be invertible, as I've said here. You can easily check that the groupoid definition of the pseudo-differential calculus has the three key properties, and as an immediate consequence, you get elliptic regularity. But now we have a plan for proving elliptic regularity for much more general classes of pseudo-differential operators, which is what we're going to do now. So again, maybe I'll pause just a sec, see if there's any questions. Oh, I see there's something in the chat. No.
Yeah, I don't think it's relevant.
Okay. All right, so let's continue on with it. So the first thing I need to do is generalize the groupoid calculus by generalizing the groupoid to calculus that works for any polynomials in vector fields satisfying Hallmunder's bracket generating condition. And for that, so like I said, the first thing we need to do is construct a tangent groupoid. And then we define our pseudo-differential calculus using exactly the same rule as before. We'll get pseudo-locality and regularity basically for free from this definition. So the only thing that will remain is the existence of parametrices. And for that, we'll need to figure out what exactly ellipticity means in this new tangent groupoid. And that will require some extra things which I may not talk about much in this talk, just for lack of time. And it uses a new notion of osculating groupoid due to Omar Mosen, who's, of course, a collaborator on this project with myself and Jakobos. And the consequence of, if we can pull off these three steps, is that you get an immediate proof of the Helffer-Nourrigat conjecture, that their operators are maximally hypoelliptic. So we need the tangent groupoid. So just let's remind ourselves where we're at. We have a manifold. We have some family of vector fields on this manifold. I'm going to write Fk for the C infinity M module generated by iterated Lie brackets of these vector fields of length at most I, of most K, sorry. One of those should be changed either. Yeah, so let's say iterated Lie brackets of the VIs of length at most K. So by construction, this filtration is compatible with Lie bracket. with the consequence that if I take the union of all the FKs, I get a filtered Lie algebra of vector fields. And we'll call this guy, if this stabilizes after some finite time, we'll call this a filtered singular foliation of depth n. And in particular, I'll be interested in the case where we have Holmander's bracket generating condition, which means that the Fn, the order n part of this will be in fact the whole module of vector fields. Okay, and you can do more general things by ascribing orders to each of these vector fields, so that some vector fields are order 1 and some are order 2 and so on and so forth, if you're so motivated. Now I need to define the osculating groups, which are going to replace the tangent bundle in our constructions. So I'll start with IP being the vanishing ideal of functions, smooth functions, which vanish at 0, and then I'll define the fiber FKP to be FK modulo IP FK. So that's just, that's what it is. It's the fiber of FK at P. Noting well that vector fields in FK may all vanish at P. So it's not the evaluation of FK, but it's some abstract notion of fiber of C infinity M module. And then we define the osculating groups to be the associated graded of this filtered space of fibers. So the associated graded here, I'm writing as the direct sum. Can't seem to select that. I'm writing as the direct sum of all the GRK FPs, where the GRK FP, in principle, it's just FKP, the fiber of degree K modulo the fiber of degree K minus 1. But you need to be a little careful here because the fibers here are not of constant dimension, and the C infinity M modules are not sections of some vector bundle, so that the quotients here can behave poorly. In particular, the inclusion of the fiber of degree K minus 1 into the fiber of degree K may not be injective because of the fact that some of the vector fields in Fk minus 1 may vanish, in which case they'll have 0 image in the fiber at Fk if the vector fields in Fk do not vanish. So that we can have dimension jumps. We can actually have an associated graded of the fiber, which is of strictly greater order than the original fiber itself. So that we just have to keep in mind. We're getting some strange bundle of fibers, which is no longer locally constant dimension. It's some very non-Hausdorff kind of vector bundle. On the other hand, there is some good news, which is that the filtered Lie algebra structure on the sections of F does descend to a graded Lie algebra structure on the fibers of the associated graded. So all of these graded fibers are in fact Lie algebras. And because they're Lie algebras, nilpotent Lie algebras, what's more, we can integrate them to Lie groups. And the easiest way to do that is just to find the Lie group as the same space, but equipped with the Baker-Campbell-Hausdorff product. So yeah, so now we have not just a bundle of Lie algebras, but a bundle of Lie groups, nilpotent Lie groups. And this is called the osculating, these are called the oscillating Lie groups. And the whole thing is called the osculating groupoid. Again, keeping in mind that these osculating Lie groups in this generality may jump in dimension from one point to the next. So here's an example, just to get some intuition of what's going on. So we'll take this hypoelliptic Laplacian of Bismuth, and we'll consider it as a polynomial in various vector fields. So I'm going to take x to be the vector field d by dx, y is going to be x d by dy, and then z will just be the Lie bracket of those. I'm going to make x order 1, y order 2, and z order 3. And we see that this generates all vector fields because z is just d by dy. We have the bracket generating condition. And then I need to see what happens in a neighborhood of a particular point, xy, to see what the fibers look like. And if the coordinate x is non-zero, then the vector field z is already a non-zero multiple of the vector field y, because the vector field y is just x times z, x non-zero. So that means that in this case, in the associated graded, the vector field z will vanish. It's already in the kernel of the quotient in degree 3. On the other hand, if x is equal to 0, if the x coordinate is equal to 0, so on this vertical axis, now z is not a non-zero multiple of y, and so it does appear as a non-trivial element in the degree 3 part of the associated graded. And we see exactly this dimension jump condition going on. So I get the following osculating Lie algebras for points off the y-axis. I get a two-dimensional Lie group, which is just abelian, because the bracket of x and y being z with z0 means it's just an abelian Lie bracket. But on the other hand, when the x coordinate is 0, I get a copy of the Heisenberg group. And this is my oscillating family of oscillating Lie algebras, or oscillating Lie algebroid, if you like. Now I need to make a tangent groupoid out of this. So this is what happened here is supposed to be what's going on at t equals 0. I need to extend this to the tangent groupoid. So, okay, pair groupoid is the usual thing. The osculating groupoid is this bundle of osculating groups with product defined fiber-wise. Again, and this strange behavior that the dimensions of the fibers will jump, so it's not a Lie groupoid, but it's not far off. It's got Lie groups as fibers in any case. And the tangent groupoid, I'll just define, at least as a set, I'll just define it in the usual way, just by family of pair groupoids, and then at t equals 0, I put the oscillating groupoid. But this doesn't explain the smooth structure, of course. I think I'm going to skip pretty quickly over the smooth structure. One way to do it very elegantly is to use the theory of Yakovos and Georges Scandalis on the holonomic groupoid of a singular foliation, because you can, by slowing down, so in this adiabatic foliation here, I have my vector fields, my generating vector fields from my singular foliation, but each slowed down by a power of t corresponding to its order. And this is an example of a singular foliation. So you can just define a singular holonomic groupoid, and it turns out this gives you precisely the smooth structure on this tangent groupoid. Okay, but I think I won't say anything more than that just for lack of time. Yeah, there's another version where you can put a topology just by saying that the following sections of the Lie algebroid, or the non-Lie algebroid, the family of derivatives, the tangent spaces to the fibers along the object space. So I have something like a Lie algebroid in this context as well, and I'm going to say that sections of this the following sections of this are smooth. I just take the retarded vector fields, again, retarded by a power of k, where k is the order of my vector field x. And when I get to t equals 0, I'll put in its class in the associated graded of degree k. Okay, and this gives me a topology, and it gives me something like a smooth structure, which is called a diffeology. A diffeological space is like a manifold where your charts are allowed to be of varying dimension and not necessarily homeomorphism, so that you get some quotient-like behavior. And it gives you some very non-Hausdorff version of a manifold. And this is the appropriate notion of the tangent algebroid in this case. And then you can use this by some exponential charts to produce a smooth structure on the tangent groupoid. And again, smooth in this weak diffeological sense, not in the usual sense of a Lie groupoid. So now we have everything in place. We have our tangent groupoid. We can define our pseudo-differential calculus. The osculating groups admit dilations just by multiplying the degree k part of the associated graded by s to the power of k instead of s. I can glue these to get a de Board-Scondolis action where I'm using exactly the same picture as before. Do I have this picture here? No, I don't have the picture here, so let me just write it. So it's again, you're just moving the copies of the pair groupoid back and forth, and you're dilating in the t equals 0. Won't let me select that. You're dilating in the t equals 0 fibers. And we can define what it means for a distribution on this groupoid to be essentially homogeneous of degree m. Okay, it's more or less the same definition. You just need to take a little bit of care because of this non-Hausdorff topology on our Lie groupoid. Now we can define our pseudo-differential operators. So henceforth, we'll suppose this bracket generating condition, and we'll just define as before a pseudo-differential operator adapted to this singular filtration to be an operator whose Schwartz kernel is the restriction at t equals 1 of one of these essentially homogeneous distributions on the tangent groupoid. And we'll denote these by psi m of f. Like I said, you get regularity and pseudo-locality basically for free. What remains to be done is parametrices. And for that, I need to understand a little about the topology. I see there's some things in the chat. Are there... okay, there are some questions in the chat. Should I answer those, or are they...
They've already been answered.
Okay, people are doing my work for me.
Taking care of business for you.
Fantastic. Yeah, so what do we need to do to get the topology on the dual bundle to the tangent algebroid? What we do is we start with a family of vector fields which are locally generating. So this is basically like a frame, except that I'm not asking that they be locally a basis, merely locally generating for the singular foliation, in which in this case this will be for the whole tangent bundle, such that it's compatible with the filtration in the sense that the first dk vector fields span all vector fields in my filtration of degree at most k, of order at most k. I then get smooth charts just by taking these retarded vector fields that I had before and multiplying them by coefficients psi I given by some parameter psi in Rd, and the same thing at t equals 0. And what happens is that now in the normal tangent groupoid of Kohn or variations due to Choi and Ponge or various other people, these maps would be local diffeomorphisms. Here, they're only locally surjective maps, but okay, it's not so bad. What that means also is that the dual maps to these maps will, instead of being locally surjective, they'll be locally injective bundle maps, so that this T star F, the dual to the tangent algebroid, which again is a bundle with jumps in dimension. It's no longer seen as a quotient space, but seen as an inclusion. So it will again be locally Hausdorff, locally compact and Hausdorff. It's just that you can have a dimension jump in some of the fibers. And these dimension jumps, again, will only happen at t equals 0, where we pass to these bizarre associated graded Lie algebras. Okay, so we have this dual space. In this case, so I see that I'm running out of time. I've vastly underestimated the amount of time. So let me think about what I'm going to cut out here. Let me just say the topology on this locally compact Hausdorff bundle with dimension jumps, as you might expect, is such that when you approach t equals 0 from t non-zero, you'll not get everything at t equals 0 as a limit of things with t non-zero. because of these dimension jumps at t equals 0, you may get some points of the fibers at t equals 0, which are just not seen by the topology from t positive. And these things are exactly the things that you need to ignore in the Helffer-Nourrigat conjecture. So I'm not going to say much more than that, unfortunately, due to lack of time. Yeah, what do I want to say about that? Maybe that's all I want to say about that for the moment. There is some, so I have some examples, which unfortunately I'll have to skip over.
Well,
which
don't panic about the time.
Oh, okay. All right. Well, then, if you give me an extra 5 minutes, maybe I'll just run through these examples because they show exactly what the topology of this space looks like. So I'm going to go back to this hypoelliptical Laplacian with the same 3 vector fields, with the same filtration on the modular vector fields, with the same osculating Lie algebras. And now I'm going to define my chart. So this is the thing that would be an actual local diffeomorphism chart in a Con's tangent groupoid, but in this case is merely a local surjection. So in each fiber, the fiber at the point x, y, t, where x and y are in my base M, my manifold M, and t is the usual parameter in Con's tangent groupoid. A, B, C here are the fiber variables. And so what I'll need to do is, again, just multiply A, B, and C respectively by the 3 retarded vector fields, X, Y, and Z, which is exactly what you get here. With the only thing you need to observe is that the Y and Z are actually collinear. The Y and Z vector fields are collinear, so that their coefficients become combined when t is non-zero. So and also when t is equal to 0, but when the x variable is non-zero, in this case the c variable would disappear. So it'll again be a surjection onto a 2-dimensional vector space. The only time you actually get a bijection onto a 3-dimensional vector space from this chart is in the fibers, these singular fibers where x is equal to 0 at t equals 0, in which case you get a map from R3 onto this Heisenberg oscillating group. Okay, so you have, at t non-zero, you have a bunch of 2-dimensional fibers here, which somehow are converging to this 3-dimensional fiber. And what's interesting about the topology is that, well, okay, so if I now take the dual space, the dual space of this 2-dimensional fiber, I have a quotient of a 3-dimensional vector space onto a 2-dimensional fiber, and the dual will be the inclusion of a 2-dimensional fiber into a 3-dimensional vector space, and it sits inside as exactly this space here when you do the calculations. So it's the orthogonal, the plane orthogonal to the vector 0tx, which is to say, if you let t goes to 0, the direction in which you approach the point 0, 0, xy equals 0, 0, will affect the angle of this 2-dimensional vector space as you come into this singular point. So that the 3-dimensional fiber at x equals y equals t equals 0, for instance, is approached by a bunch of 2-dimensional planes coming in from t positive in different directions. And it turns out that because all of these different directions are attainable for t positive, these 2-dimensional subspaces, the limits of these 2-dimensional subspaces actually sweep out this entire 3-dimensional space here. So despite the fact that you have this dimension jump, we'll still get the entire 3-dimensional fiber, so the entire oscillating group here, as limits of the t positive part. But now if I go to a slightly higher dimensional example, if I just replace the coefficient x by x squared here, and I won't do all the calculations, you now get a 4-dimensional fiber at t equals x equals y equals 0. And in this case, these two-dimensional planes coming in from T positive will sweep out some three-dimensional subset of the four-dimensional fiber, but not the whole four-dimensional fiber. So we'll end up with some subset, which is some three-dimensional cone inside this dual fiber here, this cotangent fiber, if you like. Okay, that was done fairly quickly, and I apologize for that, but let's plow on bravely nonetheless. So this is precisely what Helffer and Nourrigat had already observed, that they define this cone. They didn't call it the Helffer-Nourrigat cone, obviously, but this is exactly what they define in their conjecture, to be those points in the dual of the osculating fibers at t equals 0, which are obtained as limits of the cotangent spaces for t positive. This sweeps out some cone inside the dual of the osculating Lie algebras. And yeah, so I've already mentioned that, you know, in the previous examples, the kinds of things that you can get. Let me just say, an important lemma is that this cone that they discovered is not any old cone. It's actually invariant under the coadjoint action of these osculating groups. And what Kirillov theory then tells us is that the representations that you get, sorry, the points that you get in these coadjoint and these cotangent fibers are a family of coadjoint orbits, and these coadjoint orbits will therefore correspond to a family of irreducible representations. And these are precisely the irreducible representations that you need for the Helffer-Nourrigat conjecture. And then, you can now finish off the proof. So this is all stuff I've more or less said before. If you have a polynomial in these vector fields, you can see it as a differential operator, take a Schwarz kernel, extend that Schwarz kernel in any essentially homogeneous way to a distribution on this fancy tangent groupoid. You can then examine what the representation under any one of these Helffer-Nourrigat representations of this frozen coefficient operator is when you restrict to t equals 0. And you find that these depend only on the original operator P and not on the way in which you've extended it. If these are all left invertible operators, then you'll get an essential inverse, a parametrics, which is essentially homogeneous of degree, and that should be -m and not -1. And as a consequence, these operators have parametrices so that you obtain hypoellipticity. Okay, which is where I want to stop. I'll just mention that in the proof of this theorem, you do need this fancier version of the oscillating groups, which is actually an oscillating groupoid due to Omar Mosen. But that's a story for another day. Sorry for running over time.
No problem. Thank you very much. Oh, a little clappy thing. There we go. Are there any questions? I have a couple of questions myself. I know for a fact, because Omar told me, that in this pseudo-differential calculus, it's not the case that if an order P operator has vanishing principal symbol, it's in fact order P-1.
Yeah.
It's a defect of this singular geometry. Can you explain a little bit what's going on there and why it doesn't matter that that defect exists?
Yeah, so the reason why that doesn't matter is because, so as you see in various things that I've said here, there are choices in a lot of this. So to take what's on this slide here, for instance, in this point 1, you see that these representations depend only on P, but the actual extension that you get to t equals 0, there's a choice there, a choice that ultimately doesn't matter for the Helffer-Nourrigat conjecture, but there's nonetheless a choice. And what's going on is that, as Omar says, the fact that the principal symbol is 0 does not necessarily mean it's lower order. That is related to choices as well, that you can always make a choice by some modifications such that the operator, so the problem will be that when you take this parametrics L in my point 2, if you just take any old inverse L on the Helffer-Nourrigat cone, the difference L times k minus 1 will be simply vanishing at t equals 0. And as Omar says, that's not good enough to get degree minus 1. But you can always modify your choice of L in such a way that it is actually of order minus 1. So there's an extra step involved in finding the appropriate parametrics. First, you find one that just vanishes at t equals 0, and then you adapt that, and so that it's vanishing in such a strong sense that it's actually of lower order.
Yeah, thank you. Raphael.
Hi, so thank you very much for your talk. Actually, I'm reading the paper, so it clarifies things. I think there also work by David Haller and Melin.
Mm-hmm.
Okay.
Yeah, so I mean, I can comment on that as well. Yeah, you're right. I didn't mention either Melin or David and Haller or your own work in this talk. There's a lot of other work on hypoellipticity results for subelliptic operators. The common thread that all of those works have is that they're in what's called the equiregular case, where the singular foliations are each of the dimensions of the components of the filtration are of constant rank, so that the osculating groupoids will actually be a vector bundle in the traditional sense, and there'll be no dimension jumps. So what's different in what's going on here with the Helffer-Nourrigat conjecture is precisely these dimension jumps that you can get. You can get an oscillating groupoid now, which is no longer a bundle of Lie groups of constant rank, but can be of jumping. They can be dimension jumps in the dimension of the fibers.
But actually, Melin he considers the same case as you, but it does not prove maximal hypoellipticity. It proves only hypoellipticity. This is at the very end of its preprint. This is at the very end of its preprint. You know, the unpublished preprint.
Yeah, I know this famous
yeah, he gave me the preprint.
Published preprint. I'll have to double check that.
He was a lifting.
Yeah. Okay. Yeah. So this is the difference. Yeah. So there's also another paper that we should mention in the same direction as the famous paper of Rothschild and Stein, where they prove hypoellipticity, and they actually get some estimates for hypoelliptic operators in the case of sums of squares operators in the sense of Hormander, using again some ingenious lifting trick. In fact, yeah. So first of all, I love that trick, and now that you mention it, I imagine that Melin is doing the same general trick, that if you can prove hypoellipticity for some, in the equiregular case, by some adding of variables, you can take an operator, a more singular operator on a smaller dimensional manifold, and lift it up to an equiregular subelliptic operator on a larger dimensional manifold. This is a fantastically ingenious trick, which, like I say, already appears in Rothschild and Stein. And it's not at all dissimilar to what is going on here. So the inspiration for what we did here with Iakovos and Omar was from Androulidakis and Skondalis, their work on precisely on polynomial groupoids for singular foliations. And there again, you see that work of Androulidakis and Skondalis is based on the notion of bisubmersion. And these bisubmersions are precisely a lifting of dimensions. So, you know, Androulidakis and Skondalis weren't at all citing Rothschild and Stein. They were working on completely different problems, but the two somehow have a philosophical common point that they're both aimed at taking something singular and lifting it to larger dimensions in which it desingularizes. And this is the general principle of these diffeological spaces. Yeah, so yeah, I think that's a point well worth making.
One more question is, what about the heat equation?
Yeah, so that is an excellent question. So I think so Omar has started working on this. That much I know. There's a recent paper by I'm terrible with their names.
Yes, Colin de Verdier,
Colin de Verdier and Trela and Luc Hilaire, and they have proven heat kernel estimates for a lot of operators in this class. And so there are results that are out there, but their paper, which is a real tour de force, it's impressive work. It's very technical. It requires a lot of analytic estimates. It'd be really nice to be able to reprove their result and maybe push it further by using groupoidal techniques, a little bit like you've done for Heisenberg manifolds and like Davey and Haller did in their paper as well.
Yeah, well, what we did is that we mixed classical pseudo-differential operator with the heat kernel, if you like. The hypoelliptic operator.
Sorry, say again.
Okay, so they take the heat semigroup
on
some sub-Laplacian.
Yep.
And they multiply by some pseudo-differential operator. But it's a classical pseudo-differential operator. It's not in your calculus or in median calculus.
Okay.
So it's yeah, because they want to prove that's called a macro-local value. So
yeah, their techniques are very different from what's going on here.
But at least you could get probably a local value where you just. Well, you just look at the heat semigroup times some function, which basically amounts to look at the heat kernel. Yeah.
No, I think that's an excellent question. I don't have much more to say on it, unfortunately, but yeah, it's a very natural question to try and do the same things, like I said, that you and Davey Haller did already for these classes of operators, and see if we can get stronger results.
Any other questions?
Oh, there is a message for you in the chat.
Ah, okay. Which one?
It's not a question.
Oh, that Alan's going to watch the talk. Okay, great.
What?
He's traveling today, he said, Pastor.
Yeah, for sure.
I'm sorry I was late. I assumed it was at 2:30, so I don't know.
Any other questions?
Can I ask a question? So just for the non-experts, I was just wondering if this method gives any simple examples of operators which are hypoelliptic, which were not previously known to be so.
Well, so the question is, what does the help? Because the goal of this theory here is to prove the Helffer-Nourrigat conjecture. So the Helffer-Nourrigat conjecture was known for large classes of operators already. So the first thing to say is all the operators, in the sense that it was already conjectured that these operators were hypoelliptic by Helffer-Nourrigat, they're sort of all morally known to be hypoelliptic already, but the conjecture wasn't proven in generality. But Helffer-Nourrigat, I mean, had even proven themselves quite a lot of cases of the conjecture. So first of all, they'd proven one direction of the conjecture, the necessity, but the sufficiency of the condition was an open problem. And they proved sufficiency, I think, for when the filtration is step 2, depth 2, whatever you want to say, so that nilpotence degree 2, they'd proven it in that case. And then various other authors had worked hard to prove it in up to rank 3, step 3, and so on and so forth. So there were partial results known, but yeah, the point of this is really to sort of close the book, you know, to say, all right, now we can really say all of the operators in this class are indeed hypoelliptic. So I could give you examples of operators which fall outside this class. As for naturally occurring operators, I need to know better what, for instance, maybe I don't have a good answer for that. Naturally occurring operators, there are plenty of naturally occurring operators that fall into this calculus, like Bismuth's hypoelliptic Laplacian, the Kolmogorov operator, plenty of other things. I don't think, you know, in terms of the utility of this work, I don't think the utility of this work is in proving hypoellipticity for some arcane class of differential operators that nobody has ever seen before. I think the utility is in simplifying the understanding of why operators which we already know hypoellipticity for, simplifying the understanding of why they're hypoelliptic. It puts it in the thing that didn't exist previously as a pseudo-differential calculus, in fact. That's maybe the best way of explaining what I think is the real advance here. I don't think it's getting more examples. I think it's putting it into a pseudo-differential calculus so that you have pseudo-differential methods for hopefully proving, you know, for instance, Omar has proved index theorems for these operators, which comes very naturally out of Collins' method. And there are many other things like the kinds of things Raphael was talking about, which might be made a lot easier by the fact that, you have a full pseudo-differential calculus now and not just, you know, some hardcore analytic estimates that give you Sobolev norm, you know, a priori estimates of some particular degree. So it conceptualizes the proof.
Okay, thanks.
Yeah,
yes, just I agree with everything that Bob said. Just to add one more comment, the Helffer-Nourrigat conjecture for me is a criterion of hypoellipticity. So now we have a criterion of hypoellipticity. I think it's quite computable. These groups that Helffer-Nourrigat cone is if you give us an operator, it's not hard to compute. So I think we have now a computable criterion for hypoellipticity. That's what I wanted to say. And there are several operators like Schrödinger type operators that with singularities and so on. That, I mean, there are various types that we can work on. Yeah.
Thank you. Perhaps it's time to stop. Thank Bob once again for a great talk.